in this video we discuss the previous year question of process management part 3, as we already discussed some questions of process management related to CPU scheduling and so on. Here we'll continue that particular part. So let's discuss. The first question is we wish to schedule 3 processes P1, P2 and P3 on a uniprocessor system. The priorities, CPU time requirement and the arrival time of the processes are shown below. So we have a choice of preemptive or non-preemptive scheduling. In preemptive scheduling, let arriving higher priority process can be preempt a currently running process with low priority, and in non-preemptive scheduling, let arriving higher priority process must wait for currently executing the process to complete before it can be scheduled on the processor. So the question is that we need to solve this question by using two techniques. One is the preemptive priority technique and the second one is non-preemptive priority technique. Means in both cases we apply the priority, but according to preemptive, as we know that the nature of preemptive, if the running process is priority is less and the new arrived process priority is higher, then we need to preempt the running process. But in case of non-preemptive technique, we continue that particular running process and after execution of that, we just execute the next higher priority process. Got it? So that is the concept. Now here we need to calculate turnaround time of arrival till completion of, turnaround time means the time from arrival till completion of P2 using preemptive and non-preemptive scheduling. So we need to calculate the turnaround time of P2 by both the technique. One is preemptive priority scheduling and other one is non-preemptive priority scheduling. So here 3 process P1, P2, P3. The highest priority is of P1 and lowest is of P2. Sorry, P3. The CPU time required and the arrival time, that is in the this. So here what we can say that the CPU time required is given in second and the arrival time is also mentioned in the second, means that hours, minute and second. So definitely we need to just understand only that, because that the CPU time is also required in second and arrival time we can consider only like that is a 5 second, that is 3 second and it is 0 second. So it arrive at 0, it arrive at 3 and arrive at 5. So don't be confused with the hours and minute, because don't need of that. So first we solve by preemptive priority. So according to preemptive priority, initially at time 0, we can say that in the CPU we can allocate the process P3, because P3 is only available at time 0. So we execute that process P3. Now how much time required to completely execute this process? 15 seconds. But we know that the next process, we can say that initially at time 0 only P3 is available, so we allocate that, but we use preemptive priority nature. So the next at time 3 the process P2 is arrived and its priority is greater than P3. The priority of P2 is greater than P3. So we can execute only for 3 unit of time to this process P3, and after then we can say that after 3 unit of time, so 15 minus 3, that is 12. So at time 3 the new process, we can say that at time 3 P2 is arrived, because the time arrival time of P2 is 3. Now we can say that the priority of P2 is greater than P3, that's why we allocate CPU to P2, and in ready queue we can say that in ready queue we just store that P3 is stored in the ready queue. Now P2 is allocate CPU at time 3 and definitely it execute again for 2 unit of time, means from 3 to 5, because at time 5 again the new process is arrived and the priority of this arrived process is highest priority, because we can say that that is the highest priority. So at time 5 the new process, that process name is P1, is arrived, and definitely this process priority is greater than this running process, so we need to allocate CPU to P1, and definitely P2 is stored in the ready queue. Now P1 is the highest priority process, so definitely it will execute completely. So the total burst of CPU, that P1 is 20. So from 5 to 20, 25 P1 will finish. Now after then we check there are 2 processes P3 and P2 is available. Out of this P3 and P2, the highest priority is of P2. So we execute P2 here. Now how much time remaining of P2? So total time is 10 second and we already execute for 2 unit of time here P2. So 2 is already executed, so remaining time is 8 because 2 time is already P2 is spent in the CPU. So remaining time is 8, so from 25 to 8 means till 33 P2 is executed. Now after that P3 is only available, we execute P3. So remaining time of P3 is 12, already 3 unit is executed. So that is 33 plus 12 is 45. So we can say that at 45 all process will execute. So you can add all this 3 time, 20 plus 10 plus 15, that is 45 second. Got it? So that is the preemptive priority technique. According to preemptive priority technique, that is the Gantt chart. Now here we need to calculate what we want to calculate the average. What is the question? Question says that we need to calculate the turnaround time of P2 only. So we need to calculate only turnaround of P2. So according to this, what is the turnaround of P2? P2 is complete at 33 and the arrival of P2 is 3. So 33 minus 3, that is 30. So turnaround time of P2 using preemptive priority is 30. So the question is turnaround time of P2 using preemptive and non-preemptive. So first answer is using preemptive. So 30 second is mentioned in first option and last option and the second option also. So we can say that A, B, D, out of A, B, D any one is correct, C is not correct because turnaround time of P2 using preemptive is 30. Now we need to check for non-preemptive also. So for non-preemptive, if we execute using non-preemptive, so here we can say that first at time 0 the process P3 is available and we execute P3, and definitely we need to execute completely P3 because it is non-preemptive in nature. So the time completion time, we can say that total CPU time of P3 is 15, so 0 to 15 P3 will execute. Now when P3 is in execution, all the process, remaining process P1 and P2 is arrived in the ready queue, and out of this two definitely the priority of P1 is greater than P2, so we execute next P1 and then P2. So that is the order of execution. So P1 is execute that for 20 unit of time, so that is 35, and after then P2 execute for 10 unit of time, so that is 45. So P2 is finished at 45 and it arrived at time 3. So the turnaround time of P2 is 45 minus 3, that is 42. So we can say that turnaround of P2 in preemptive is 30 and in non-preemptive is 42. So 30 and 42, the option D is correctly satisfy both the data. Got it? So D is the right answer. So that is very easy question. Now the next question, consider the following processes with the arrival time and the length of CPU burst given in milliseconds. The scheduling algorithm used is preemptive shortest remaining time first. The average turnaround time of this process is, so what you can say that consider the following process with the arrival time and the length of burst. Got it? The scheduling algorithm uses preemptive shortest remaining SRTF. So average turnaround time we need to calculate. So just consider this SRTF technique, that is preemptive in nature. At time 0 only P1 is here, so we allocate CPU to P1 at time 0. Now definitely the next process arrive at time 3, so till 3 P1 is continuously execute. Now at time 3 P2 is arrived in the ready queue. Now the remaining burst of P1, that after execution of 3 unit of time the remaining is 7 and new arrived process burst is 6, so definitely 6 is less than 7, so we need to execute P2. So allocate CPU to P2 and we preempt the P1 and store in ready queue. Now P2 is execute for how much time? So next arrive process at time 7 and here the current time is 3, so definitely till 7 it will execute completely. Means we can say that whatever the duration, that 6 is required, and from 3 to 7 means 4 unit of time it run from 3 to 7, total 4 unit of time it used the CPU. So remaining burst of this P2 is 2 and at time 7 P3 is arrived and their burst is 1, so definitely 1 is less than 2, so we need to preempt P2 here and allocate CPU to P3. Got it? P2 is in the ready queue, and definitely P3 required exactly 1 unit of time, so it will execute completely. Now at time 8, the next process P4 is also in ready queue. Now there are two processes sorry, that P1 is also in the ready queue. So there are three processes, P1, P2 and P4 is in the ready queue. The burst of P1 is 7, remaining burst. The burst of P2 is 2, remaining burst, and the burst of P4 is 3. So the smallest burst process is P2, and then P4, and then P1. Because all processes in the ready queue we arrange one by one. Now for P2, how much time? 2. So 8 plus 2, 10. For P4, there are 3, so 13, and that is 7, so that is 20. Got it? So you can add all that, 16, 17 plus 3, 20. So total 20 time at which the process, all process will finish. Now we need to calculate average turnaround. So just find out P1 is execute finally at 20. So turnaround time for P1 plus P2 plus P3 plus P4. So what is the turnaround of P1? Complete at 20, arrive at 0. 20 minus 0 plus. For P2, complete at 10, arrive at 3. So 10 minus 3, that is 7. For P3, complete at 8, arrive at 7. So 8 minus 7 plus. For P4, complete at 13 and arrive at 8. So 13 minus 8, divide by 4. So we can say that 20 plus 7 plus 1 plus 5. So 20 plus 10 minus 3 is 7, 8 minus 7 is 1, 13 minus 8 is 5. So divide by 4. So that is 27, 28 plus 5, 33 by 4. 4 8s are 32 and 4 2.5. 8.25 is the right answer. Got it? So 8.25 millisecond is the average millisecond for this average turnaround time for this SRTF technique. Got it? So that is the correct result, 8.25. Now next question is, consider n process sharing a CPU in round robin fashion. Assume that each process switch takes a second. What must be the quantum size q such that the overhead resulting from the process switching is minimized, but at the same time each process is guaranteed to get its turn at the CPU at every t second. So in this question, what the question asks that there are n processes in the CPU. We can say that there are n processes, and we use the technique like round robin fashion, and each process switch takes a second. Means when we allocate a process, context switching is performed when we allocate a process, first P1, and from P1 to P2 it requires a second, from P2 to P3 it required a second, for P4 it requires a second, and definitely when you execute a P1, so that is means when you allocate CPU to process, it required overhead of s second. Got it? Now what must be the time quantum size q such that overhead resulting from the process is minimized, at the same time each process is guaranteed to get its turn to the CPU at least every t second. Means we want to minimize the time, minimize the overhead. Overhead means what? Overhead means that time that required to allocate the CPU to a particular process. Got it? So we need to minimize that, and we must ensure that every process get its turn after every t second. Got it? So we need to identify the value of q. What is the minimum value of q we need to require to satisfy this condition? So just understand by the example. So here what we can say that there are n processes P1, P2, P3 up to Pn. Now definitely when one process is allocated to the CPU, it required s second for the allocation, that is overhead. Got it? Now it execute time quantum like q time quantum for their execution. After then it preempt and the P2 process arrive, it again execute for q time. P3 is arrive, it again execute for q time. P4 is arrive, it again execute for q time. So what we can say that till Pn all the processes execute for q time, and after then P1 is again arrived. Got it? So we need to check that the value of this it should be equivalent, means the total time that required by executing all this process and plus overhead to allocate the CPU to this process, that should be equivalent to, or we can say that the less than or equals to the T time, because at least T time we required. So in this case, what we can say that here, just understand that first we can say that the P1, after then total, before getting the turn P1 again, total n minus 1 process is execute from 2 to n. So definitely that is n minus 1 process. So that is n minus 1 process that execute after P1 and before P1 again. Got it? And each n minus 1 require q time quantum. So we can say that n minus 1 into q. That is the fixed time that required to execute n minus 1 process. Now the overhead. Definitely we need to add overhead also in this. So we can say that after P1, when you allocate q, so 1, 2, 3, 4, 5, 6 up to n minus 1. N minus 1 overhead is required because each time it required s second. So n minus 1 second plus 1 overhead when you again allocate CPU to P1, means either you count this one or you can last one. So definitely total n process overhead is need to calculate. So n into s means after this complete time we can able to allocate, we can say that we can able to start the execution of P1 again. Got it? So that is the total time. So what we can say that this total sum should be less than equals to T, because we need to execute this in T second. We need to arrive the turn of P1 again in T second. So that is the equation. Just solve this. You can get the value of Q. So that Q into n minus 1, we can rearrange this. That less than equals to T minus ns. This n into s is go in the right hand side, and that is this. So Q is less than equals to T minus ns divided by n minus 1. So T minus ns divided by n minus 1. So A is the right answer. Got it? So that is the logic to solve such type of question. So A is the correct answer. Now the next question. For jobs to be executed on a single processor system arrive at time 0 in order ABCD. Their burst CPU time is this, and the completion time of A under round robin scheduling with time slice of 1 time unit is. Got it? So there are 4 processes ABCD and the burst time of this process is 4181, and on a single processor arrive at time 0. All processes are arrive at time 0 in the order ABCD. Now in the order ABCD means we need to execute first A and then B and then C and then D. Means first we allocate CPU to A, then B and then C and D for 1 unit of time slice, because it is round robin. So here we need to maintain ready queue and definitely running state. So initially ready queue contain this 4 process in this order ABCD. Now here we need to execute the processes for 1 unit. The completion time of A under round robin, we need to calculate the completion time of A under round robin. Got it? So initially what we can say that all process contain the burst greater than or equals to 1. So for 1 unit all process will execute. So that is this from 0 to 1, 2, 3, 4, because time slice is 1. Now after then again the turns of process will occur, means when A will finish, A is again allocated to the ready queue. Now the burst time of B is exactly 1. That's why B is not again allocated to the we can say B is not stored in ready queue again. When it finished for 1 unit of time, its computation is finished. Now C, so definitely C is again add to this list, and D will completely finished. D is completely finished because the burst time of D is also 1. Now we have only 2 processes A and C. So we can execute alternatively A and C, because A required 4 and C required 8. So when the 4 slot of A will finish, we'll stop that also. So AC, again AC, again AC. Got it? So you can say that 1, 2, 3 and 4. So here A will finished. So you just increase by 1 because it is the time slice 1. So 4, 5, 6, 7, 8, 9. So at time 9 the process A will finished. Got it? That very easy question. So you just allocate one by one A, B, C, D, and after then only A and C is exist. So AC slot will continue. So definitely 1, 2, 3 and 4. 4 slot of C is also finished. Now after then what we can say that after when the A is finished here, the C is completely finished in this slot. So 1, 2, 3. So remaining time of C is, that is 5. So 9 plus 5, that is 14. So at that time the complete all process will finished. So you can add, the sum should be 14. So 4 plus 5 plus 8, 13 plus 1, 14. So that is correct. So at time 9, A will finished. So answer D is right. Got it? Now the next question. Consider the following CPU process with arrival time in millisecond and the length of CPU burst in the millisecond, except for process P4 as given this. Means that burst time for process P4 is not given. Got it? So arrival time and the length of CPU burst in given except for P4. The burst time of P4 is not given in this quiz. So that is a process and their arrival time is this and this is the burst time. Got it? So that is just a table, the data according that if average waiting time across all processes 2 millisecond and preemptive shortest remaining time first scheduling algorithm is used to schedule the process, then find the value of X. Means average waiting time of all process across all process is 2 millisecond and preemptive shortest remaining time first algorithm is used. So SRTF is used, and what we can say that here that average waiting time is given but the burst time is not given. We need to calculate the burst time of process P4. So just understand the execution of this. What we can say that here at time 0 only P1 is in the system. So P1 is allocated to the CPU at time 0. Now how much time P1 will execute? Definitely just say understand P4 is arrive at time 4. So till 4 don't worry about that execution. Definitely till 4 we need to execute this 3 process. So using SRTF we execute first this 3 according to SRTF logic. So definitely what we can say that here the 1 unit of time P1 will execute, the remaining time of P1 is 4 and at time 1 P2 is arrived and their burst is 1. So definitely we allocate P2 and at time 1 we execute P2 and definitely it execute for 1 unit of time because there is exactly burst is 1. So P2 is finished completely. Now at time 2 there is not any other process in ready queue because P3 is arrived 3 and P4 is arrived at 4. Only P1 is available, so we need to execute P1 again. Only 4 we can say that total burst is 4. Got it? And when we execute 1 unit of time, the remaining burst of this P3 when we execute for 1 unit of time. So the remaining burst of P1 is 3 and at time 3 P3 is also arrived and the burst is also that is 3 only. Got it? So what we can say that we can continue the execution of this P1 only. Either you increase this value or you can execute completely. So again we execute for 1 unit of time. Got it? Why we execute for 1 unit of time? Because at time 4 P4 is arrived and the burst time of P4 is now X. Just understand the burst time of P4 is X. So in this case what happened, we can say that now either you can execute P1. Just understand the logic of how many process is in the ready queue, that P1 is in the running and definitely P2 is already finished. The remaining time of P1 is how much? That 1 unit, 1 and 1. Total 2 unit is executed here, total 3 unit. So we can say that here the remaining time of P1 we just mentioned here. From 5 there are 3 slot of P1 will execute. So remaining time of P1 is 2. Remaining time of P3 is 3 and the P4. So definitely P3 and P4 is in the ready queue and the time of P3 is 3 and we don't know about P4. So time of P4 is X. Got it? So there are two ways. Either we can say that the value of X is definitely if we execute, we definitely sure about that P3 is not execute in this slot because the remaining time of P1 is less than P3. So either P1 is execute continuously or we can execute P4. Got it? So if we execute P1 continuously in this case, got it? If we execute P1, so in this case what we can say that the average waiting time of all process is 2 millisecond. The average waiting time is 2 millisecond. So here we can say that if we continue the process P1 and finish this execution till 6, got it? Just understand the concept. We execute P1 completely. Now we have a process P3 and P4 in our we can say that ready queue. So if we consider P4 and then P3, or we can say that the P3 and P4. If we consider P4 first, so if we return P4 after P1, we just assume that P1 completely execute. So what burst you can consider here at place of P4? Just understand the logic here at that time, only understand at that time. So we execute P1 till 4. Now remaining burst of P1 is 2. Burst of P3 is 3. That is greater than 2. So definitely P1 is executed before P3. Now if we put the value of P4 2, if we assume the value of x is 2, so at that time what happened? Just understand. If we execute P4 first, if we execute P4, so definitely the value of P4 we consider less than 2. If we consider it exactly 2, so we can say that the P1 is continuously executed because the burst of this and this is equal. We just assume the value of x is equals to 2 with this option. Got it? We just consider the value out of this 1 to 4, we just consider 2. So if we consider 2, the value of P4 is 2. We can execute P1 continuously because the burst of this new process and the running process is equal. So we continue the running process. Now after that, we execute P4 for 2 unit of time and then execute P3 for 3 unit of time. So that is 11. Means we put the value of x is 2. Got it? Now here that is the result. Now find the average waiting. We can say about we need to find out average waiting time. So here in this case, the what we can say that the P1 process, what is the waiting time of P1? So P1 first arrive at 0 and allocate 0, so there is not any wait in this case. Now here we can say that after that P1 allocate CPU at time 2, it preempt at 1 and allocate at 2. So waiting time of P1 is 1 unit in this slot. After then P1 is completely finished. So 1 waiting time of P1 plus what is the waiting time of P2? So P2 is finished in this slot, allocate at time 1 and arrive at time 1. So there is not any waiting for P2. Now what is the waiting for P3? P3 is allocate at 8 and arrive at 3. So 8 minus 3, that is 5. So that is waiting of P3. Now for P4, CPU is allocated at time 6 and it arrive at 4. So 6 minus 4 is 2. So if you add and divide by 4, so 1 plus 8 minus 3, that is 5 plus 6 minus 2, that is 6 minus 4, that is 2. So divide by 4. So 7 and 8, 8 by 4, that is 2. So the average waiting time we need to says that the 2 milliseconds. So yes, it is 2 milliseconds. If you consider the value of x is 2, then average waiting time is 2. So definitely you can consider this 2 value. So you can put 2, 1, 4. So whatever you putting, either you we can say that we just assume that we need to put any value of x and then calculate. So when we put the value of x is 2, the average waiting time is exactly 2. So the answer is 2 is correct. So the value of x is 2. That is the right answer. Now the next question, which of the following scheduling algorithm may cause starvation? Out of this 4, which of the following may cause starvation? So again, just understand the point of starvation. First come first serve. In this case, if there is any starvation, so definitely starvation is not possible in first come first serve. So by default, if we can say that the starvation is occurred due to the preemptive nature of the scheduling, because we can say that in SJF, in round robin priority, shortest process next, shortest remaining time first. So in this case, what we can say that if we use SJF, got it? If we use SJF, then we can say that in this new arrived process, less arrived process again and again arrived, and definitely the large process will be in the large size process will be in the waiting. So in non-preemptive, SJF can cause the starvation. Got it? Here what? According to option, we can say that first come first serve is not possible, so A will be removed. Now that round robin and priority, shortest process next, so definitely shortest process can generate the we can say that the in this case starvation is possible, because if smaller process arrive, then large size process will wait for long time. Priority can also generate the, we can say that the starvation, And shortest remaining time is can also generate the starvation, because in shortest remaining time again same, either it is preemptive or non-preemptive, both cases starvation is possible. But round robin is also not generate any starvation, so we can say that C, D, E is possible, so B option is correct. So for A and B, if you remove A and B, then option only B is exist here, because first come first serve and round robin somehow it is related, because in round robin we assign the time slice of the CPU to each and every process. It is time sharing operating system, so definitely in which each process get its turn, so starvation is not possible. And first come first serve is also follow the same logic, because if process is arrived in ready queue, definitely it allocate to the CPU after some time. So only C, D and E can cause starvation, so the answer is B. Now the next 5 job A, B, C, D are waiting in a ready queue. Their expected running time is 9, 6, 3, 5 and X respectively. So here what we can say that the process A, B, C, D and E, the running time is 9, 6, 3, 5 and X. All jobs enter in a ready queue at time 0, all are present in the ready queue. They must run in which order to minimize the average response time? If X is to minimize the average response time, means we want to get fast response. So X is less than 5 and greater than 4. So definitely the value of X according to this equation is exactly 4. Got it? So when you put the value of X equals to 4 here, to get the fast response we need to execute the job definitely, because it execute each job exactly one time, means it use the non-preemptive nature, and in the non-preemptive we can use the shortest job first for the best result. So C first execute C and then E and then D and then B and then A. So C, E, D, B, A according to their increasing order of their burst we can arrange, because shortest job first can execute can generate fast response. So C, E, D, B, A. So B is the right answer. For that we can say that B is correct answer. Got it? Very easy question. Now the next, consider the following 4 processes with arrival time and the length of CPU burst given in the millisecond. 4 processes with arrival time and length of CPU is given. Average waiting time for the preemptive SJF scheduling algorithm is, what is the average waiting time? So in this case what we use preemptive SJF. Preemptive SJF means it discuss about the SRTF. Got it? So first at time 0 only P1 is available. We execute P1 for how much time? Exactly 1 time, because at 1 the new process arrive, so we need to compare that. So after that remaining time of P1 is 7 and P2 burst is 4, so definitely burst of P2 is less, so we need to execute P2 next. Now after 1 unit of time P3 is also arrived, but the burst of P3 is greater than this, so definitely we execute P2 continuously. And after then the next process after P2, P3 and P4 both burst is greater than P2, so definitely the minimum process is P2 only, so it will finish completely. So how many burst? 4. So 1 to 5 it will execute completely. So at that time when P2 finished, remaining part of P1, P3 and P4 all process in the ready queue. This 3 process in the ready queue. What is the P1 burst? 7, P3 burst is 9 and P4 is 4. So definitely P4 is 5. So the minimum is P4 and then P1 and then P3. So first we execute P4, then P1 and then P3. Got it? So first execute P4 and then P1 and then P3. So what is the P4? The burst is 5. So 5 plus 5, 10. Remaining of P1 is 7, 17. P3 is 9. So that is 26. So when you add all this, 8 plus 4, 12. 12 plus 9 is the 21 plus 5, 26. So execution is correct. Now we need to check average waiting time. So how to calculate the average waiting time? So just understand the logic. First P1 is allocated time 0, arrive at 0. So there is not any waiting initially. But here P1 is preempt the resource CPU at time 1 and again allocated time 10. So during this time the P1 is in the waiting. So 10 minus 1 is 9. So the waiting time of P1 is 9 plus that is the waiting time of P1. Waiting time of P2, the CPU is allocated to P2 at 1 and arrive at 1. So there is not any waiting of P2, that is 0. For P3, CPU is allocated 17. For P3, CPU is allocated 17 and it arrive at 2. So 17 minus 2 is 15. So that is the waiting time of P3. And for P4, CPU is allocated time 5 and it arrive at 3. So 5 minus 3, that is 2. Now divide by 4. So that is 9 plus 15, 24 plus 2, 26. Got it? Divide by 4. So 4 6 are 24 and 4 5s are 6.5. So 6.5 is the average, we can say that the waiting time of preemptive SRTF scheduling. Got it? So that is the answer, 6.5 average waiting time. Very easy question, just need to calculate carefully. Now consider the CPU intensive process, that time is 20, 10, 30 unit respectively, arrive at time interval 1, 3 and 7. Suppose operating system is implementing SRTF preemptive scheduling, then how many context switches are required? Suppose context switching at the beginning of ready queue and at the end of ready queue is not counted. So that is very easy question. There are 3 processes and the bus time of this process is 20, 10 and 30, and arrival time of this process is 1, 3 and 7. We use SRTF technique, shortest remaining time first. We need to implement, suppose operating system implement SRTF preemptive scheduling, then number of context switching required. So first arrive process is P1, so first execute P1, and definitely that is use SRTF, shortest remaining time first. Got it? So first P1 is arrived and the burst of P1 is 20, and after then at time 3 we can say that it start at time 1. So we just written here 1. Now after then that 1 at time 1 P1 is start, and at time 3 means 1 plus we can say that 2 after 2 unit of time, when we execute P1 2 unit of time, the burst time of P1 is 20. So the remaining is 18. So we can say that the new process burst is less. So definitely we execute P2 in this slot. Now the burst of P2 is minimum, that is 10. The next process at time 7 that arrive, that burst is maximum out of this 2. So definitely P2 will finish completely. So that is 3 plus 10, that is 13. Now at time 13 we can say that there are 2 processes P1 and P3. The burst of P1 is 18, remaining burst of P1 is 18, so we execute P1 and then P3. So here we need to calculate only the context switching. So the first, second, third, 4 and 5. There are 5 context switching. Out of this, first and last will not count according to the question. So there are only 3 context switching, 1, 2, 3. From P1 to P2, from P2 to again P1, and from P1 to again P3. So this 3 context switching is required. So the answer is 3. Total 5 context switching, out of that first, beginning and last is not counted. So the answer is 3. 3 context switching are there. Got it? Now in the system using single processor, a new process arrive at the rate of 6 process per minute. In a system using single processor, a new process arrive at rate of 6 process per minute, 6 process per minute. Got it? 6 process per minute is arrived in the system, and each process requires 7 seconds of service time. So burst time of each process is 7 seconds. So what is the CPU utilization? So how to calculate such type of question? So the question says that there are 6 processes that arrive in 1 minute, and each process requires 7 seconds for the execution. So in 1 minute, we can say that in 1 minute there are 60 seconds. Definitely we know that in 1 minute how many seconds? 60 seconds. And in 1 minute 7 processes arrive, and each process requires 6 seconds. So in 1 minute total we can say that 42 seconds is required to execute 7 processes. In 1 minute, there are 6 processes per minute. We can say that 6 processes arrive in per minute and each process requires 7 seconds. Got it? It is just reverse, the result will same. So, 6 processes arrive and each process requires 7 seconds. So, total 42 seconds required to execute 6 processes in 1 minute. So, out of this 60 seconds, CPU is utilized for 42 seconds. Got it? Because in 1 minute 60 seconds, and out of that 60 seconds, 42 seconds is utilized by CPU to execute a process, and remaining we can say that the how many seconds, that is 18 seconds, is definitely the CPU is ideal. So, what is the CPU utilization? So, out of 60, 42 is utilized. So, that is the answer. Multiply by 100 because it is in the percentage. So, we can say that 0 cancel out, 7 6 are 72, 7 6 are 42, and 7 into 10 is, that is 70. So, it is 70%. So, the answer is 70%. So, how many CPU utilization? So, 70% is that. It is simple logical question. Now, next question, which of the following statement is not true for multi-level feedback queue processor scheduling algorithm? Multi-level feedback queue, as we already discussed about that. So, queue have a different priority, multi-level feedback queues. Which of the following is not true? So, definitely it is correct. Each queue can be maintained with different priority. Each queue may have a different scheduling algorithm. Yes, it is also correct. You can use different scheduling algorithm. Process are permanently assigned to a queue. Means a particular process is permanently assigned to a particular queue. So, definitely it is not correct according to that, because it may possible process allocate to any one of the process, any one of the queue. It is not dedicated. Got it? So, it is not always true. This algorithm can be configured to match a specific system under design. To configure a match a specific system under design. So, that is possible. But C is not correct. Got it? So, it is simple theoretical question. So, C is not right answer. So, we can say that what is the correct answer? C is correct because it is not true for multi-level feedback queue. Now, the next question. Consider the 3 processes with arrival time and the CPU burst time in millisecond. Arrival time and CPU burst time is given in millisecond. The Gantt chart for a preemptive SRTF scheduling technique. The Gantt chart is given this. Now, which of the following is correct Gantt chart for SRTF? That is the question. A, B, C, or none of this. So, according to SRTF, what we can say that first we execute at time 0, P1 is there, definitely. First we execute P1 at time 0 and it execute for 1 unit of time, and after that the remaining burst of P1 is 6 and P2 is arrive at 1, their burst is 4. Definitely it is minimum process. So, we need to execute P2 second and the burst of P2 is minimum out of this 3. So, P2 will execute completely for 4 unit of time. So, that is 5. Now, after then P3 is arrive at time 2 and P0 is already exists. So, burst of this 2 is minimum is P1. So, next execute P1 and then P3. So, remaining time of P1 is 6 and remaining time of P3 is what? That is 8. So, that is 19. Got it? So, P1, P2 here we just need to check the order P1, P2, P1, P3. So, the option B is correct. P1, P2, P1, P3. Got it? So, B is the right answer. That is very easy question. Next question. The following table show the process in the ready queue and the time required for each process to complete its job. The burst time and the name of process is mentioned, that all are in the ready queue, means all are present in the ready queue. In round robin scheduling with 5 milliseconds is used, what is the average waiting time of the process in the queue? So, by round robin technique we need to execute one by one each process that is in the ready queue. So, definitely you allocate each process, we can say that the ready queue contain, so first all process from the ready queue, first P1 and then P2 and then P3 and then P4 and then P5, all process one by one allocate. Again we start the turn of P1. Got it? Because we just count that one by one, because if all process already in ready queue, so you can directly run the process one by one. Got it? So, for 5 unit all burst is greater than or equals to 5. So, P1 execute for 5 unit. Now, how many burst of remaining of P1? That is 5. Now P2 execute for 5 unit and P2 will finished. Now P3 execute for 5 unit and the remaining burst of P3 we written here, that is 15. Remaining burst of P1 is 5, we written in above side to remember that point. Now next P4 execute for 5 unit. So from 8 if we subtract 5, so there are 3 unit remaining. Now P5 execute for 5 unit. So from 15 if we subtract 5, so remaining is 10. So here we can say that the P2 is completely finished. Now the P1, P3, P4 and P5 is remaining. So we again put in this order P1, P3, P4 and P5. That is the way to written. Got it? Because first P1 executes, so definitely again next turn P1 is occur, then P3 and then P4 and P5, because P2 is completely finished. P2 is completely finished. Now P1 execute for 5 unit of time, so that is for 30 and it will finished. P3 execute for 5 unit of time and total 15 is remaining. Here 5 will execute, so remaining is 10. P4 is execute for 3 unit of time because 3 is only remaining part. P4 is execute completely. P5 is execute for 5 unit of time, so 38 plus 5 is 43. Remaining time of P5 is 5. Now there is only two process, P3 and P5. So we execute one by one. First P3 and then P5. So P3 required, again it execute for 5 unit of time and remaining is 5 because 10 is remaining here and we execute 5 unit here, so 5 is remaining. Now P5 is execute completely, 48 plus 5 is 53 and P5 will finish. Now only P3 is exist here, so we execute P3 here in last up to 58 and P3 will finish. So you just add all this value, it should be equal to 58. So is it 58? So 10 plus 5, 15 plus 2, 20, that is 35 plus 8, 43 plus 15, 43 plus 5, 48 thus and 10, 58. So that is correct. So now we need to calculate the average waiting time of the process. So just how to calculate the average waiting time? So definitely either you add all the slots or in this case in the round robin you just find the turnaround of each and every process and subtract the burst from turnaround. So definitely you can easily calculate the waiting time. So first for P1 process, when the P1 is finished, just find the last slot where P1 is execute. So P1 is executed in this slot and it will finish. So at time 30. So 30 minus for P1 we calculate turnaround time. Got it? So P1 30 minus what is the arrival. So we can say that exactly all process arrived at the same time, 0 time. We assume that all process arrive at 0 time. So definitely there is no subtraction, that is by default turnaround. So P1 turnaround is 30. P2 is finished at time where P2 is completely finished in this slot. So at time 10. P3 is finished at which time? That is 58. P4 is finished at which time? That is 38. And P5 is finished at which time? That is 53. So that is a turnaround. Out from this turnaround, if you subtract the burst, then you get the waiting time. So minus 10, the burst of P1. So that is 20. That is the waiting time. This is the turnaround time and this is the burst time that we subtract. Got it? So here 30 minus 5, so that is 5. Now from 58 minus 20, so that is 38. Got it? Now 38 minus 8, that is 30. Now 53 minus 15, so I think that is 50 minus 15, that is 45. And sorry, 35 plus 3, 38. So that is 38. Got it? So just add all this and divide by 5. So that is 25 and 38 plus 30, 38. So we can say that 20 plus 30, 50, 55. That 55 plus 38 plus 38. So 8 plus 8, 16 plus 5, 21 power 2. 3, 6 plus 5, 11, 12, 13. 131 divided by 5. So 5 2s are 10 and 5 6s are 30. 5 2s are 10. 26.2 something is the right answer. So B is the correct. 26.2 millisecond is the right answer. Got it? So that is simple maths. You need to calculate carefully, and that is the way to log, because it is arrival is 0, and to calculate the waiting time, and if the process execute in multiple slots, so directly you find the turnaround and subtract the burst, you get the waiting. And here all arrive at the same time, 0 time. So definitely the last process P3. So turnaround of P3 is 58 directly. You can calculate like this. So answer is B. Now the next question, consider the following set of process with arrival time and the required CPU burst time given in millisecond. So here that is the arrival time and this is the burst time, and that is the process ID. Got it? So this is the table. Now what is the sequence in which the process are complete? Assume round robin sequence with the time quantum 2 is used. So we need to calculate the sequence in which the process finished. Only we need to calculate sequence. So we use the round robin fashion. So initially P1 is arrived. Got it? So we can say that we allocate P1 process for 2 unit of time because 2 millisecond is required. So total burst of P1 is 4, remaining is 2. When P1 execute for 2 unit of time, P2 is arrived. So we execute P2 and P1 is goes to the ready queue. Just understand, when P1 time out, P1 go to the ready queue and P2 is in the CPU. Now when P2 is execute for 2 unit of time, means till 4, P2 will finish completely, and the new process P3 is in the ready queue. At time 3 P3 is arrived. Now P1 is execute because next process turn is P1 for 2 unit of time and P1 will finish. Now finally only P3 is exist, P3 is execute for 1 unit of time and P3 is finished. So that is 4 plus 2, 6 plus 1, 7. So total time is 7. That is correct. Order of execution is P2, P1, P3. Last 3 slot will give 3 process. So P2, P1, P3. So that is P2, P1, P3. B is the right answer. That is very easy question. Got it? Now the next, consider the set of process with arrival time, CPU burst time and the priority are mentioned. Now none of the process have IO burst. The waiting time in millisecond of P1 using preemptive priority scheduling algorithm. We need to apply preemptive priority scheduling and want to find the waiting time of process P1. What is the waiting time of P1? Preemptive priority. So here what we can say, that set of process with arrival time in millisecond, CPU burst in millisecond and priority where 0 is the highest priority, that is mentioned here. So it is highest priority process. So definitely it is lowest priority process. Got it? So according to the number, 0 is highest priority. Now initially first P1 is execute because P1 is arrive at time 0, and definitely the priority of P1 is 2 and the next process at arrive time 5. So 0 to 5 only P1 is in the system, till 5 only P1 is in the system. So we execute P1. So when you execute for 5 unit of time, the remaining time of P1 is 6 and at the time of 5 P2 is arrived. Got it? So P2 is arrived and definitely the priority of P2 is highest. So we execute P2 for how much time? Complete time, because P2 is highest process. So whatever the process is arrived, we need to execute P2 first. Got it? So P2 execute completely. So 28 plus 5, that is 33. Now till 33 all the processes in the system, means P2 is finished, but P3, P4, P5 and the given process P1 is all are in the system. Got it? P1, P3, P4 and P5 in ready queue. When P2 finished at that time, after this when we go to the ready queue, this 4 process exist. Now according to their priority, arrange the process. So the P0, P2 is already calculated. Now from P0 we can say P2, after P2 P4 is highest priority. So we execute next P4, because you understand the logic, because all are exist in the ready queue. So P4, after then we execute P1. After then we execute P2 is already executed, P4 is executed, P1 is executed. Now we execute P3 and then P5. P3 and then P5, because P5 is lowest priority process. Got it? Because they arrive, definitely P2 is arrived, P4 is arrived before P3. Got it? And P5 is arrived before P3. But during the execution of P2, when P2 completely execute, all the processes arrived, and either they arrive before or after, we just need to calculate the priority. So according to priority we assign. Now for how much time P4 execute, that is for 10 unit of time, so that is 43. Now remaining time of P1 is 6, so 43 plus 6, that is 47. We need to calculate only waiting time of P1. So waiting time of P1, so how to calculate the waiting time of P1? So here we can say that P1 initially, P1 does not wait any time, arrive 0 and allocate. Now 8 time 5, CPU is preempt from P1, and again 8 time 43, CPU is allocate to P1. So that 43 minus 5 is the waiting time of P1. So that is 38. So the answer is 38. For 38 time process P1 wait. Don't need to solve complete question because we need to check only the waiting time of P1, and P1 finished here. So we can say that either you just subtract 47 minus arrival minus burst. So 47 minus arrival. So definitely there is not any arrival, so 0. So turnaround time is 47 minus burst. So if you subtract the 47 minus 11, so I think that is okay. So that is 43, and after then we execute for 6 unit of time. So 43 plus 6 is 49, not 47. We just written by mistake 47. But the answer is 38 is correct because we calculate by this value. If you calculate by this value, then 49 minus 11, that is 38. Definitely the answer is always same. So 38 is the correct answer. So that is all about the questions of CPU scheduling, and we can say that the process management related with CPU scheduling and the process state diagram. Thank you.